The title of my talk today is Stable, Wavelength Tunable and Flat Optical Frequency Com Generation from an actively and harmonically mode-locked fiber laser using a short bismuth-based nonlinear erbium-doped fiber. The author is myself from Tokyo University of Science. This is outline of this talk. First of all, I am going to talk about background and purpose of this presentation. Optical frequency com generators can offer many attractive applications, such as multi-wavelength laser sources, ultra-short pulse generation, arbitrary waveform generation, ultra-fast signal processing, and optical frequency difference. Several methods to generate the optical frequency com have been proposed and demonstrated so far. Among many com sources, harmonically mode-locked fiber lasers are a popular candidate. However, the range of the wavelength tunability is normally limited to the conventional wavelength band because these fiber lasers usually employ silica-based erbium-doped fibers as the intracavity gain media. In addition, it is also difficult to generate a frequency com with good spectral flatness. So the purpose of this talk is to review a technique for generating wavelength tunable flat frequency com and signal pulses from a harmonically mode-locked fiber laser employing a bismuth oxide-based nonlinear erbium-doped fiber. This is outline of this talk. And next, I am going to explain the experimental setup for evaluating the performance of the bismuth-based frequency com generator. This is the experimental setup. A 1.5 meter long bismuth oxide-based nonlinear erbium-doped fiber supplied from Asahi Glass Company Limited was used as the intracavity gain medium. The erbium concentration was 3,250 ppm. These 980 nanometer laser diodes were used for the forward pumping and the backward pumping, respectively. These optical isolators ensured the unidirectional cavity. Harmonic mode locking at 10 GHz was achieved using a lithium niobate intensity modulator driven by a synthesizer. We did not employ a variable optical delay line at our hand. Instead, we adjusted the modulation frequency to achieve optimum mode locking operation. These polarization controllers were used to adjust the polarization state. A spectrally broadened flat frequency com was also generated by using the self-phase modulation in the bismuth oxide-based nonlinear erbium-doped fiber. The nonlinear coefficient gamma was as high as 64.2 per watt per kilometer. The total length of the fiber ring cavity was 8 meters. The cavity length could be essentially shortened to 3 meters because the total length of the fiber pigtails was 5 meters. However, the long cavity generally results in instability due to the large supermode noise. To suppress the supermode noise, several stabilization techniques have been proposed and demonstrated so far. These employ Fabry-Perot semiconductor optical amplifiers, and nonlinear fibers. Particularly, the use of cell phase modulation in the nonlinear fiber and spectral filtering by the optical bandpass filter is an attractive technique for stabilization. In this scheme, higher intensity pulses are spectrally broadened by the cell phase modulation and then suffer higher loss through the optical bandpass filter. Therefore, fast intensity limiting is achieved and the pulse intensities can be stabilized. In this experiment, to suppress the supermode noise, we also used the cell phase modulation in the 1.5 meter long bismuth oxide-based nonlinear erbium doped fiber and the spectral filtering by a bandwidth variable tunable filter supplied from Alnea Laboratory Company Limited. These are characteristics of the bandwidth variable tunable filter. This tunable filter had an ideal flat top filter profile and a sharp filter edge roll-off of about 200 dB per nanometer. The filter center wavelength was tunable over the C band and the L band, and the 3 dB filter bandwidth was independently variable from 0.2 nanometer to 10 nanometer. Optical power was coupled out of the cavity through a 10% output coupler. The output was monitored by an optical power meter, an optical spectrum analyzer, an intensity autocorrelator, a radio frequency spectrum analyzer, and a 63 GHz sampling oscilloscope. In addition, back-to-back bit error rate measurements were also performed in a 10 gigabit per sec return to zero system. A lithium niobate intensity modulator modulated the output pulse intensity with a 10 gigabit per sec pseudo-random bit sequence from a pulse pattern generator. The generated 10 gigabit per sec signal pulses were monitored by the sampling oscilloscope. The bit error rate was measured as a function of the average power at the input of an erbium doped fiber preamplifier. Next, we go on to the experimental results and the discussions. Firstly, I am going to explain these basic output characteristics for the bismuth-based frequency comb generator. This figure shows an optical comb spectrum at the center wavelength of 1580 nanometer when the filter bandwidth is 2 nanometer. Due to the high nonlinearity of the bismuth-based fiber, the spectrum is flatly broadened and flat combs with an interval of 0.08 nanometer corresponding to a repetition rate of 10 GHz are clearly seen. The 10 dB spectral width is 1.92 nanometer with 24 comb lines, which corresponds to a frequency bandwidth of 240 GHz. This figure shows the corresponding autocorrelation trace. The full width at half maximum of the output pulses is 7.1 picosec. This figure shows the corresponding RF spectrum of the 10 GHz laser output. Because of the high nonlinearity of the bismuth-based fiber, a dominant supermode is clearly seen, and unwanted beatings are not observed. This figure shows the corresponding sampling oscilloscope trace. The pulse interval is 100 picosec, which corresponds to a repetition rate of 10 GHz. Due to the high nonlinearity of the bismuth-based fiber, the supermode noise is suppressed efficiently and the pulse intensity is very stable. This figure shows the average output power measured as a function of the center wavelength. The output optical power ranges from minus 1.98 dBm to 4.24 dBm, and the center wavelength can be tuned from 1540 nanometer to 1620 nanometer. This wavelength tuning range of 80 nanometer covers both the C band and the L band. The wavelength dependence of the output power is mainly attributed to the gain profile of the bismuth-based nonlinear erbium doped fiber. Therefore, the output power can be increased, and the tuning range can also be broadened if we use the pump lasers with higher output power. This figure shows the 10 dB spectral width of the output frequency comb, measured as a function of the center wavelength. The filter bandwidth is optimally adjusted in the range from 1 nanometer to 2 nanometer so that the spectral width of the output comb is maximized while keeping stable pulse intensity. The SPM effect is proportional to the intensity of each optical pulse, amplified depending on the wavelength in the bismuth-based nonlinear erbium doped fiber. Therefore, the spectral width of the output comb has also similar wavelength dependence and becomes to the maximum value of 2 nanometer at the center wavelength of 1565 nanometer. This figure shows the corresponding pulse width characteristics. The pulse width of the output is almost independent of the wavelength and ranges from 7.1 picosec to 8.3 picosec. Secondly, I am going to explain the system performance of the bismuth-based frequency comb generator. This figure shows the I patterns of the modulated 10 gigabit per sec signal pulses for various wavelength center wavelengths. The pulse interval is 100 picosec, which corresponds to a repetition frequency of 10 GHz. The pulse intensity fluctuation due to the competition between the supermodes is not observed, and clear eye opening is obtained. This figure shows the corresponding bit error rate characteristics, and these are the receiver sensitivities for various center wavelengths. Good bit error rate performance without any indication of error flow is realized. This figure shows the receiver sensitivity measured as a function of the center wavelength. Receiver sensitivity is from -36 dBm to -28.9 dBm over the entire wavelength tuning range. Next, we discuss about the long-term operation. In our measurements, we could maintain error-free operation for at least 10 minutes without any adjustment of the system. The period of stable operation is mainly attributed to the variation of the polarization state and the temperature-induced cavity length change. Therefore, both a polarization maintaining configuration and a cavity length stabilizing system are required to achieve the long-term performance for optical communication systems and their processing applications. This is outline of this talk, and finally, I summarize this presentation. In conclusion, we have reviewed a technique for generating an optical frequency comb from a 10 GHz harmonically mode-locked laser, employing a 1.5 meter long bismuth-based nonlinear erbium doped fiber. The cavity length has been as short as 8 meter because of the short bismuth-based fiber. By utilizing a wide gain profile of the bismuth-based fiber, a tunable wavelength range of 80 nanometer has been achieved. The optical comb spectrum has been flatly broadened up to 2 nanometer due to a high nonlinearity of the bismuth-based fiber. The supermode noise has also been suppressed sufficiently. Thus, bit error-free operation has been realized over the entire tunable wavelength range. Thank you very much for your kind attention.